started. Okay, so this session is about how you can test the your models, basically looking for errors. I don't say correctness because technically you can't. It's very hard to prove that something's correct. And typically what you're trying to do instead is, can you find errors? So, you know, sort of like we assume that the absence of errors means that at least we have some more assurance that we have verified and validated. A lot of the thoughts here are drawn from experience over the last half century with the software industry. And so I'll actually start by giving sort of some context in terms of what the software industry has done with verification and validation. And then we'll make the rather challenging transition from, you know, what people do with software to what does that mean for our models as we develop our models. The way I've organized the materials, it's similar to what we had yesterday, and I'm trying to be sensitive to the significant diversity in the folks participating in this short course. That some people really have had no background in programming, and so a lot of the more detailed technical parts on the programming may be coming more slowly. And others, may have considerable sophistication. So trying to pay attention to both audiences. What I think is that the intent is with this first slide deck, which really lays out more of the concepts. This should be of interest to everyone, and we'll sort of lay some foundation here. And then some of the later material, especially exercises, may be more appropriate for a subset that has more of the technical background in the software technical background. Okay, so let me go ahead and start out with the context in terms of software. So in software, there are several different kinds of testing that the software industry has found productive. This has been sort of a difficult evolution over the last half century or so. Early on, you can make actually some interesting analogies to where modeling is in, especially kinetics modeling is in for biomedical models versus software. The complexity of biomedical models today, kinetic models, if you have something on the order of, a few hundred reactions, that's a really big model. It's a real challenge to fit all the pieces together. The metabolic models, which, the like flux balance analysis, those can be much bigger, several thousand reactions. But this is really comparable to the kind of complexity that you would see in software in like the early 1960s. Where, if you make the, sort of equivalence between a reaction and a statement in a program, that's about what you would have. And the techniques that are available at that time for software testing were relatively modest. Basically, you try running it, and if it doesn't fail, looks good. As time went on, and over the last few decades, of course, software, the complexity has grown tremendously to now where you have literally millions of lines of code. And to be able to deal with that level of complexity, a lot has been developed to basically have software that's software that's reproducible and reliable and reusable. So let me go through some of the things that are involved here. So first of all, there's this distinction between what's called static error checking and dynamic error checking. The static error checking is shown here in the middle. What static means is that you're doing some error checking without actually running the program. And I'll get to that in a minute, but this has some interesting analogs to looking at biomedical models as well. The areas on the outside here are all what are called dynamic checking. That means is you're actually running the code to be able to check it. So I'll go through a few of these that are relevant for what we're looking at today. So the static errors, we'll definitely take a look at that. and there are some techniques that are very interesting in terms of what you might do with checking your model without actually simulating anything. And then there are these other parts over here that I'll discuss in terms of analogs. So unit testing means that you typically develop software in terms of distinct modules, which has potentially an analog in for biomedical models. You could organize things by parts of a cell, by reaction pathways, by organs. There are a lot of different ways you can talk about sort of modules. And unit testing refers to what tests can be done at the level of that unit. System testing is about what you do to evaluate the model as a whole. And this is typically what you would do. I mean, I think this kind of testing, I think, is common for biological models. Anything that's published, you'd want to be able to show the relationship between model predictions and what you got from wet lab results. That'd be comparable to what system testing means in software. So I'm not going to talk so much about system testing because I think that concept is one you're very familiar with. I think anybody who's familiar with looking at literature in that involves any sort of modeling, we'll see that kind of testing going on, that kind of evaluation assessment of a model. Unit testing is actually sort of interesting because you're looking for characteristics that are consistent with your expectations. And what does that mean in terms of modeling? So that's a little bit different twist on things. What I would like to do is give you a feeling for what's involved in software when you talk about putting together tests. And just to give you a sense about what does it mean if we're going to incorporate some kind of testing capability into our models? How much does that demand? I mean, the short statement is that typically, if you write 1,000 lines of code, you're probably going to write about 1,000 lines or more of tests. Test codes as well. It's usually around 1-to-1, sometimes a little bit more, sometimes a little bit less. Yesterday, I introduced this package SP Stoat that we use for parameter estimation, and I thought that might be a useful piece of software then to discuss about how it's structured in terms of amounts of lines of code and also the amount of lines of tests. So the package codes themselves are about 26 modules and about 6,000 lines of code. The test codes, these are mostly unit tests. They're about 33 modules and about 4,000 lines of code. So roughly, it's 40%, close to half. And when you talk about tests in software, and this is sort of, maybe raises some thoughts in terms of what it means for models as well. What you're interested in is the interaction between these various units. These, they could be modules, they could be methods. And what a lot of times is of interest is, what's called the call graph, who calls whom. And this has sort of an analog potentially to in a biomedical model, which pathways are interacting. And to be able to do a test, you might want to make sure that all the interactions that you expect are present. So we talk about static errors. I mentioned before, static error is something that you can detect without actually running the code. And so in software, one example of this is if you have a path in your code where a variable is undefined. So for example, in this particular statement right here, there's a test up here checking for some random number, wants to do something a certain fraction of the time, and an assignment is made. This is sort of just sample code to illustrate a point. So if this test is true, you'll assign a value to this variable they called thing. However, if the test is not true, you did not assign a value to this variable. And in which case, when you got down to here and print this variable, it would be undefined. Now, this is something you certainly would detect if you ran the code a few times. Obviously, it's a random number, so it wouldn't happen every time. It happens some of the time. But static error checking allows you to analyze the code here. And so you can detect this immediately with one of these static checks. And that's the analog we're looking for biomedical models. Unit testing is usually what we taught. Yeah, that mentioned that before. That's where you have separate modules that you've developed. We might have separate models that we've developed, for example. You want to have separate tests for each one of them just to ensure they work separately in isolation. This is extremely valuable because typically errors, the whole thing with figuring out errors is a problem of isolation. You want to get down to the smallest fraction of code that contains the error, because the larger the amount of code you have to examine to look for the error, the harder it is to find. And typically with unit testing, the goal is to make sure that you have unit tests that are sufficient so that every statement in your program gets executed in at least one of the tests. That's the unit tests we have over here, and the way you structure a unit test. And I know this may seem overly detailed right now, but you'll see how this comes into play in what we are proposing in terms of testing models as well. So typically you're going to have some code that performs a kind of function. In this case, this is code that does something related to plotting. So this is the function. You've seen this before. It has arguments of various sorts. And then you will have a separate test then that runs this function and does so under different conditions, exercising these arguments, assigning different values to these arguments to make sure these various different paths through the code get executed. So this is what's done today with software testing. And I mentioned before the whole thing with system testing, just to give you the analog for what was done with SB Stoat. So the system test for SB Stoat was to run through most of the curated models and biomodels and see if by creating synthetic observational data and then trying to estimate parameters from those synthetic observational data, do we come up with reasonable estimates of the parameters? Or at a bare minimum, there are no exceptions. That's pretty low bar, but hopefully come up with reasonable values for the parameters. And that's the way the system testing was done for SB Stoat. All right, so that's what's done with software. Let's get on to biomedical models and what does testing mean there. I'm going to start with static testing. There's actually quite a bit of static testing that's available for models, and there are some other systems. There's one I'll mention in passing, Moiety, that has quite some extensive array of tests that are done. Moiety is specific. It does the focus there is really on a metabolic models, especially flux balance analysis, which does not include kinetics. And so the area of looking for errors in kinetics models is covered much less. I think at this point, I think that's somewhat of an open area. How do you do testing of the kinetics formulas? But one of the areas that I think everybody would agree with is having to do with some of the elements of the way the reactions themselves are formed. So on the assumption, and this may be a false assumption, that folks are following along and looking at the slides and not looking at actually the slide deck. You're seeing me that I'm going along. What I'd like you to do is take a minute and look at this model. And very simple, what we've got is, a simple representation of ATP synthesis and hydrolysis. Now, what do you see? I'll tell you something's wrong with it. Anybody see what appears to be wrong with this model?
Is antimony able to do E, or is it only powers?
I'm sorry, could you repeat that, please?
Yes.
Oh, the E down
E
here?
-5 is actually a valid antimony syntax, yeah.
Yeah, that is a valid. So I will tell you this model, there is no antimony error in this model. This model will run in antimony. So that's just so that folks are looking for the right thing. It's not a syntax error or anything like that. This is a conceptual error in the model itself.
Polly points out that there's a missing initial condition for PE.
Okay, that's fair. Okay, that's fair. I mean, the default is it's going to end up being 0. That's a fair statement. That's actually not and I'll tell you that this is what's in these classes of static models, static errors. This is an error that would be detected without actually running the model. Okay, so let me give you folks a little bit.
People have
Go
been
ahead.
pointing out in the chat. It's like, wait, like there ADP to ATP does not require P also. So yeah, P should be part of J1.
Okay, P. Okay, yes, that's exactly the error. And as a result of that, what you have a situation where the inorganic phosphate grows without bound because we're creating an inorganic phosphate and we're never consuming it. So you're not going through this sort of futile cycle of synthesis and hydrolysis. So that's exactly the error. And these kinds of errors are pretty easy to introduce in subtle ways. The general statement that people usually use for this class of errors is a mass balance error, and we'll have some more detailed discussion about what does that really mean. I mean, concept, we all know what that means. You should these are chemical reactions, not nuclear reactions, so you should preserve the atoms on both sides. So conceptually that's there, but we'll get into a little more detail. That's exactly what the issue is that we have treated the inorganic phosphate in an inconsistent way, and certainly have not accounted for it in J1. So that's the reason why it creases without bounds. And so, exactly the error that was exposed in that discussion. So let's go through some analysis of what is mass balance. Now, clearly, mass balance seems like a very reasonable requirement for any model. And what we just saw there was clearly an issue. So go through this. We saw before. I mean, presumably this one over here. If we just say ATP goes to ADP. We haven't accounted explicitly for the inorganic phosphate. This is not necessarily wrong, though. It's very common when you write down a reaction that you assume something about the environment in which the reaction takes place. You may just assume there are a lot of inorganic phosphates around, and the rates of these reactions are such that the concentration of those inorganic phosphates aren't going to change. So I'm not going to explicitly include it. And that's very commonly done. But, formally, of course, this is imbalanced.
Joe, we have one question for the chat real quick.
Yeah.
Says, would it be helpful to think in terms of biological errors versus math model errors? Or perhaps the distinction isn't as clear cut in certain cases?
Oh, okay. Yeah, I would say I've been referring to these as conceptual errors. You could say that I would say, or model errors. I think biological error, my interpretation of what you're saying is it is a conceptual error in the domain of the modeling. And that's exactly right. I mean, I guess technically these are probably more biochemical errors or even chemical errors. But yes, right. And that's a distinction from the math, I would say, becomes a little bit trickier when we start talking about kinetics, because you're going to have a formula describing rates, and then a common error that you might encounter is you suddenly have negative concentrations, because is that a biological error? Is that a math error? I don't know, but any case, that maybe that's more discussion than this really requires. Okay, so if we look at this reaction here. ATP goes to ADP plus an inorganic phosphate. Is that mass balanced? Actually, let me take a look at see, if you have thoughts on this, enter them into the chat, because I would do the best we can to be interactive, or voice them directly. What you're thinking in terms of, is this mass balanced? I hear some typing. I don't know from whom. Okay, any thoughts on this one? Well, this is interesting. The issue is that if you look at the details of the chemical structures, once you break the bonds between the beta and gamma inorganic phosphates, you're going to end up with some extra atoms in there, some hydrogens and a couple of hydrogens and some oxygens. And also there's some technical questions about the chemical environment, about, you know, where you do or don't have protons attached to the inorganic phosphates. But ignoring that part, at least you're breaking bonds. And so this is probably, if you add up the atoms, or if you add up the atoms, you're not going to come up with the same counts. And that's why it's hydrolysis, right? You know, you need water in there too. So, you know, technically you probably have to have something more like this. But again, you know, there's some quibbling over here based on the chemical environment about, you know, where the protons are. So this, you know, this would be mass balanced. You could count them all out. So I guess then the next question comes in, okay, gee, you know, ATP hydrolysis, it seems like a relatively simple reaction. You get into more complicated reactions, especially involving large molecules that, you know, could be in various states of, you know, methylation, acetylation, you know, who knows what, protonation. Do we really have to count all of that stuff to, you know, make sure that we're mass balanced, so that we could essentially have a semantic check of our our reactions, and make sure that we don't end up with weird stuff like, you know, inorganic phosphate increasing indefinitely? And I think that's a very good question about, you know, where are the boundaries are there and what level of checking has to be done. So that's what we have over here, you know, is true mass balance always desired? So there are basically two schools of thought on this one. One of them is an approach, it's called atomic mass analysis, which really does try and count all the atoms on both sides of the reaction, make sure that they add up. And if they don't, then, you know, gives you a warning and you should try and go and fix it. And there's another school of thought which is a little bit less restrictive, and that's what's called for. It's more of a kind of consistency check. Now, to see that one, let me go back over here to this model here that we know was incorrect, and we saw what was going on with the inorganic phosphate. See, the issue here is partly that this is, you know, there's not a mass balance over here, as we know from just the previous page. I mean, even this one here, we should add in water and, you know, make sure that, you know, things come out right. But let's say we ignore the water part for a minute. The issue is that we included phosphate over here in the hydrolysis, but in the synthesis, we don't include the inorganic phosphate. And so you could argue to some extent that, you know, it's not so much a matter of being mass balanced as being consistent. You know, if I'm consistently going to say that I have these inorganic phosphates in my solution and the concentration isn't going to change, then fine, J0 should be ATP goes to ADP. And yeah, that's silly because they're really not the same mass. But if I have enough of these inorganic phosphates around, maybe that makes sense. And, you know, certainly it's not going to affect how I do my kinetics involved over here. Whereas if I want to make sure that, you know, the inorganic phosphates, maybe they're a critical part of how these reactions actually proceed, I should include phosphate down there in J1. So that's sort of the second philosophy, is that consistency check. So what I'm going to do is I'm going to introduce two approaches that sort of correspond to these, you know, two ways of dealing with this. And you know, hopefully this doesn't seem like super overkill on the topic of mass balance. But on the other hand, mass balance is one of those things that really is a core check on our models, and something that can be done without running the models. And as, you know, someone who's had experience with both modeling, you know, biochemical modeling, then also with software, I'll tell you these static checks that, you know, you can figure out an error before you actually run the program, it's hugely helpful. That's just a tremendous amount of lost time that you avoid. Now, okay, so let's talk about, for the first one is, let's try and actually achieve some kind of balance. Now, I mentioned atomic mass analysis, where you actually try and balance the atoms. That can be a bit cumbersome. It can lead to unnecessarily detailed specification of reactions, especially for some bigger molecules. So probably, at least my intuition on that one is I don't think it's practical in many cases, although people do it. So they manage to figure their way through it. But I think that there are other choices. So in chemistry, it's very common to think of sort of functional groups, for a molecule. This notion of a moiety, a collection of chemical species, it's really a substructure that have a particular function. And the nice thing about the concept of a moiety is that you can view the structure has some flexibility. When you say it's a moiety, you can have some slight variations in the actual chemical structure. You can have a proton here, or the proton isn't there. Some little things that might change, and that gives us some flexibility in terms of looking at whether or not something is balanced. So we're not talking about so much mass balance as much sort of a structural balance or a moiety balance. So if we look at this over here, all of these, phosphate groups, inorganic phosphate groups, are examples of, these are all examples of an inorganic phosphate, but they have very different character, they actually have different atomic structures. I mean, like this gamma phosphate over here, has, 2 hydroxys, and then this, the oxygens over there, but that's a bit different from, the beta. The beta doesn't have the 2 hydroxys. So, and then we have the inorganic phosphate in solution, which again, I show it protonated, it could be deprotonated. So that gives us this flexibility. And now we can talk more about, a balance from the point of view of structures. So the idea with moiety analysis is you're looking for balance of the moieties on both sides of the reaction. So let's give an example, keep our running example here with ATP synthesis and hydrolysis. So if we look at, here's the way to read this table over here. So here are the molecules, ATP, ADP, and then I'm calling the inorganic phosphate a molecule in of itself. The moieties I'm referring to, so this is the adenosine, and then we've got the inorganic phosphate. So obviously inorganic phosphate, just has inorganic phosphate in it. ADP has 2 of them, ATP has 3, and both ADP and ATP have 1 adenosine. So now that's sort of this analysis of how do I sort, a molecule into its component moieties. Then if I look at a chemical reaction, like ATP goes to ADP plus inorganic phosphate, now I do the analysis of basically just counting up the moieties. So I have an adenosine and I have an inorganic phosphate moiety. This has ATP has 1 adenosine, 3 inorganic phosphates. ADP plus the inorganic phosphate has the same counts. These are all equal. So at that point, it would say it's moiety balanced. I mean, as we know before, this is true. This is not technically mass balanced because I'd have to include water in there, but it is moiety balanced. The other thing that you can do with this, which is very convenient, is if you're in a situation where you decide that the inorganic phosphate is actually implicit because of my chemical environment, well, you can decide, at that point, gee, maybe I should just write it as ATP goes to ADP. Of course, this wouldn't be technically moiety balanced if it isn't moiety balanced in terms of if I do this arithmetic over here. But what I can do is, since the inorganic phosphate is considered implicit, I can just not count that row because I'm not really considering it. And in that case, it is moiety balanced. So that's another flexibility that you get there. The main challenges with moiety analysis is that you need the moiety structures of the molecules that you're dealing with. There are many different ways you can address this, but this is not commonly available. We have chemical structures of small molecules, like with, I think Lucian, you went through Chebby or today, or I don't know if you went through
I
the
didn't
databases.
actually do that. No, sorry.
Okay, all right. Well, there are many resources available for you, chemical resources that will give you the atomic structure of small molecules. Big molecules are more of a challenge, in part because they can be in so many different chemical states. But small molecules, you can get that, whereas you don't necessarily get a moiety structure for it. So, you know, that would have to be supplied in some way in order to make this useful. Although, like I said before, there are ways you can get around this. You see, many people will write their models and actually use names of molecules that represent their moiety structure. I did an analysis of biomodels, and I think on the order of 10 to 15% of the models, actually people would write it down in terms of a moiety structure. So, it's useful, but probably not the dominant way to do it. And then the other thing that you need to do is be able to relate. Then once you see a chemical species, you have to know what it is so you can figure out its moiety structure. So this is an annotation problem. I think elsewhere, I don't know. Have we already talked about annotations?
I
Yeah.
feel like
Yeah, okay, fine. So annotations are something that exists, that concept exists already. So that probably is less of a barrier, but you still need the moiety database. So, you know, even if you've annotated, then what's the moiety database for what is it? So that becomes still the challenge. So those are sort of the roadblocks for using moiety analysis. My feeling about it is that, you know, if you're writing a new model, and there are various ways you can have sort of an explicit expression of the moiety structure. You can sort of do this from the names, and then just your naming convention will allow you to do this kind of checking relatively easy. And there's some tools actually that will help you with that. So anyway, but that's one approach. Now, like I said, the barrier here is that there is some work either upfront or after the fact that the modeler has to do to be able to do moiety analysis. The next approach to, please, go ahead.
To go back to that previous slide real quick.
Yep.
Are there systems that would, even if they don't know anything about it, they would see the first reaction and then they would flag the second reaction as wrong because it's not the same? Like if you go from ATP to ADP plus P, it just knows you can't go backwards with just ADP because you don't have the P that you had before. So even if it doesn't know anything about biology, it can still figure out the problem.
Well, you know, so but you, well, I'm not too sure what you're after. I mean, if you you would have to know something about what these chemical structures are. I mean, if these are isomers, for example, you know,
all you know in this case, like you would know that ATP, the first one sets up that the right, if the left and right are the same.
Yes.
Then if the second one implies that P is 0, because the left and right, if the left and right are the same at the top in the first reaction and the left and right are the same in the second reaction, if you just solve the math, then P is 0. And if you say that P can't be 0, then you can just say that, right?
Okay. Well, thank you for the segue, actually, because that's the next approach.
All right, excellent.
and that's a great observation, right? That there's an inconsistency here, even if you know nothing about what these chemical structures are, and you make the assumption, which I think was implicit in what you're saying, Lucian, that you know all molecules have non-zero mass. And the mass on the left-hand side has to equal the mass on the right-hand side, then, you know, P must have non-zero mass, you know, and so that means that the mass of ATP has to equal the mass of ADP plus P. But over here, we're saying the mass of ADP equals the mass of ATP. So obviously here, ATP has to be larger than ADP. Here, they have to be equal. So that's inconsistent. So, and that's actually a technique called stoichiometric inconsistency. And this is a paper that from a while ago, from 2008. This technique is actually fairly widely used even now. And I'll talk about it, you know, how it's structured. There's a bit of formality around it, but what the nice thing about it is that you can do this checking for that kind of inconsistency without knowing anything about the structure of the molecules in the reaction network. The downside of it is that, you know, if I just looked at J1, if I don't have J0, if I just look at J1, I have no idea if that's right or wrong, if that's mass balance. Because what I'm looking for are inconsistencies. I need J0 and J1 to detect the error. But whereas with an atomic mass analysis or a moiety analysis, I could tell just by looking at J1 where the error is, that there's an error. Another somewhat subtlety with this, which we'll talk more about it later, is that this approach, this inconsistency checking approach, can find that an inconsistency is present, but it doesn't tell you anything about where that inconsistency is. So if you have a reaction network with 100 reactions in it, it can tell you, yeah, you got a problem, but give you no clue as to what you need to fix. And, you know, as our reaction networks get larger, that's really unhelpful. So anyway, let me go through this, because there's an answer to that second part about, you know, figuring it out. And that's actually some work that, follow-on work that a colleague of mine have pursued. Okay, so detection of stoichiometric inconsistencies. This idea came about some time ago. And this is exactly what Lucian was just alluding to, exactly this example. And he did this without reading my slides in advance, I think. So this is awesome.
Just
all right.
flowed naturally.
Yeah, it just flows naturally, I guess. Yeah, right. Okay, so here's the idea that the way you detect one of these inconsistencies is that you're trying to figure out, and this is sort of the formulation of the problem you're looking for. It's a bit of a proof by contradiction is what you're doing. I mean, if you think in that framework, I think it really helps in terms of figuring this out. So here we have 3 chemical species. And if this is consistent, if there's no inconsistency, then I should be able to find a mass for ATP, ADP, and inorganic phosphate such that there is no sort of logical inconsistency that results, exactly the way that Lucian before was reasoning about this. And so if you go through this, what does this mean if I have these 3 masses? It means that the mass of ATP has to equal the mass of ADP plus the mass of phosphate. And the fact that all these masses have to be positive, and all these masses are positive. And reaction 2 says that the mass of ADP has to equal the mass of ATP. So that means M2 equals M1. And then obviously that means that, you know, M3 would have to be 0, but that's a contradiction. So that's the way that determine if there are any masses greater than 0 that satisfy that. And the conclusion is there is no such vector that, you know, no such mass that is present, because M3 would have to be 0. Or others would have to be negative, which also is unacceptable. So that's the way this thing works. Now, what makes this useful, I mean, this is a nice framework to work in. It's very, very clear. You're looking for inconsistencies. It doesn't require any prior knowledge, which is a big deal, because although you should annotate your models, it may be that you encounter a model you'd like to use and it's not annotated, and so you'd like to at least check it to see if, there are any inconsistencies present in the model. And so you would like to do that without having to annotate the model and then find out you're not going to use it anyway. So this, this is a very useful kind of capability to apply. The question is, how do you do this in a way that's very efficient and doesn't require a lot more work on your part? So let me show you how to do this. I guess this one here I was teeing up just because the ATP example, which we've been working with, it's sort of obvious. You take a look at this one, it's not so obvious. I mean, and this is only 6 reactions. You can imagine if you have 100, it's not at all obvious that there's a problem here. But if you go through the analysis, what happens, so I guess I don't solve it here. I'm going to go through. So what I'm going to do now is the way we're going to approach this. I guess what I wanted to do is tee up that there is an issue here with trying to figure this out. It's non-trivial, even for a small reaction network. And so the way we're going to solve this is something called linear programming. Again, I know this audience is diverse. Many of you, this may actually be the first time you've encountered this phrase, linear programming. I'll tell you that this doesn't mean, it has nothing to do with Python programming. This is a historical term having to do with a way of formulating certain mathematical problems. It's actually related to optimization, which we talked about yesterday, but I don't want to get on a sidetrack about that. The only reason why I mention it is that these are well-established techniques that exist in computer packages. I'm going to give you sort of a peek of what's under the cover on these packages, but you will actually not even have to worry about doing anything with linear programming. You will just essentially point a Python package at your SBML model, and it will come back and say, you have an error or you don't have an error. And so it's that part would be simple, but I'm trying to give you a sort of a peek inside about what goes on. So what I'm going to do on the next slide is give you a one-page summary of linear programming. It'll be relatively quick, nothing very fancy, nothing very mathematical. Show you how this gets interpreted in a way to do this stoichiometric inconsistency checking. And then we'll go through some examples. So when you look at a linear program, we'll just go over here. The way the formalization of a linear program is, the reason why it's called linear is you divide things up into two parts. You have an objective function, and this was part of our discussion actually yesterday when we were talking about SP Stoic. We talked about an objective function and constraints. So the objective function is some linear function of something that are unknown. So in our case, the masses are unknown. We're trying to figure out, can we find these masses? We're going to minimize the some constant times these masses. Actually, in our case, the A sub k's, you can ignore this. I probably should have a line through it. These are all going to be 1, so you only have to worry about that. We're trying to minimize this. Now, we don't actually don't care about the minimization. The thing that we are going to care about are the constraints. So this actually technically is what's called a feasibility problem. We just want to see if we can find the constraints. What we care about is, as we look at these expressions for the different reactions, if you look at it and look at what's going on there for mass balance, we have we want the mass on the left-hand side equals the mass on the right-hand side, and then they're weighted by their stoichiometries. And so the B's over here, these are the stoichiometries, and you have one of these equations for each reaction. And that's all that's going on here, and the MKs are these unknowns. These are unknown masses. And we want to see if it's feasible to find one of these M's, given what the reaction expressions are. So go through an example over here so that this makes a little more sense, hopefully a little less abstract. So here's our running example of ATP, okay? And what we're going to do, we've got, this is this one over here, remember, and I assume that definitely there's been an introduction to the stoichiometry matrix. Is that true, Lucian?
I think so. I think I remembered.
Yeah, a little bit.
Yeah.
Yeah, a little bit. Okay. So this information comes directly from the stoichiometry matrix, which, by the way, is something that when you write an antimony model, Tellurium will figure out. You have the stoichiometry matrix available to you. That's actually calculated implicitly. So just by writing the model. So the way that the matrix works is anything that's a reactant has a negative associated with it, and anything that's a product is positive. And then there potentially is, there could be a number in front of here as well. If there are multiple molecules of the same type that are either part of a reactant or a product. So in this case, what that would do is that affects the mass then that you would have over here. So in our case over here, for ATP goes to ADP plus inorganic phosphate, there's a minus for the M1 for the mass of ATP because that's a reactant, and we're gaining mass in ADP and inorganic phosphate. And we're saying is that these masses have to be assign values such that they sum to 0. And similarly for the reaction over here, where obviously ADP it's the same mass index. So it is going to then be a negative over here because it's a reactant, and ATP is then going to be the positive one. So these are the constraints. And what we want to do is we want to solve a feasibility problem where we determine whether or not these constraints can be satisfied. And another, you can have both equality constraints in linear programming and also inequality constraints. And our inequality constraint is all these masses are positive. And that's the setup for this. I'm not going to talk any more about linear programming, just to say these are widely available tools. Linear programming has been around since, I think it's the late 40s or so. There's a fellow by the name, well, I guess I don't know if it was linear programming or it was integer programming, but there's a fellow I worked for years ago at IBM Research named Ralph Gomery, who's very involved with this area. Linear programming has been used widely for things like airplane scheduling and other kinds of scheduling problems. Linear programs can scale to huge numbers of these variables. And so this is, a very efficient way of actually checking reaction networks that are much larger than we use today. So there's really no, generally speaking, these are relatively efficient kinds of procedures. So that's the sort of the general way that we can do this kind of stoichiometry, is checking for stoichiometric inconsistencies. Okay, and then as I said before, that's from the Stoichiometry Matrix, which again, if you write your SBML model, your model is representable in SBML. We can read it into Tellurium. We get the Stoichiometry Matrix, and then we can figure out these constraints. Fairly straightforward. Okay, so that's the stoichiometry. This is a little bit more detailed about how it's constructed. I'm not going to go through all this level of detail. Okay. So as I mentioned before, the key challenge with stoichiometric inconsistency as it was originally formulated in the 2008 paper is that it gives you a binary answer. Yes, I'm consistent, or no, I'm not. And if I'm not, well, it's your time to try and find the needle in the haystack. So there's some work that I was involved with later on, with the last couple of years, something called a graphical analysis of mass equivalence sets. And this particular piece of work, it does the same idea of detecting stoichiometric inconsistencies. But what it does is it also gives you information about which reactions are involved in the inconsistencies. So you have a chance to figure it out. If we go back, here's the kind of analysis that gets done with this games piece of work. Woo-Sub Shin is the primary originator of this. It's really his intellectual efforts that created this algorithm. And so what games allows you to do is, if you present it with this reaction network, it would give you essentially a proof of why it is that this is inconsistent. And the proof is sort of the logic behind which reactions are involved. So for example, it would say that ADP must be, the mass of ADP and ADP must be equal because of this reaction, the J1 reaction, this uni-uni reaction. But ADP has to have a mass less than ATP because of this reaction. And from this, it concludes that there was an error. So that way you've isolated, in this case, it doesn't help because there are only two reactions. But in a larger network, this is a big deal. So let's see what happens, apply it where. So I gave you this as a teaser from before. By the way, did anybody figure out the stoichiometric inconsistency here? I'm just curious if there was any comment on that, say, hey, I know what it is.
No one saw it in the chat, no.
No, but okay, fine. I didn't see anything. Just curious. All right. So I'm going to give you more of an annotated summary of this rather than exactly what the output. We could show you the output at some point from games. So what it does the same kind of analysis as we've seen before. It looks at the molecules on each side of the reaction. To see, because this implies some inequalities. So this over here implies, this set of inequalities And then what you see is because of these are equalities over here, it says that these three molecules must have the same mass. But you see right here that 154 has to be less than 160. So again, it discovers the error. And the approach that's taken to this is this sort of graphical analysis. And I'm not going to go through a lot of detail here, just to give you sort of a flavor for it. Again, this is all about having some feeling about what's under the hood. I don't know about you, but I'm not an expert on automobile engines. But, I like to know a little bit. So if a mechanic tells me, something, it makes sense. So anyway, that's all I'm trying to do here. So the basic of the algorithm, and I said this is focusing on the G for the graphical part, is that we're going to form a graph where the nodes in the graph are molecules that have the same mass. And we call these mass equivalent sets. That's this part over here, the ME, we abbreviate that MES, mass equivalent sets. And how do we know they're mass equivalent? It's because of these uni-uni reactions. If it's uni-uni, they should be mass equivalent. And then we relate nodes to one another based on the reactions. So for example, V537, so over here, that says that we go from C160 to C86. So that means that this mass should be, in this case, because it's uni-uni, they should be equal. It's actually in the set. Let's take V601. Those are both, oh, I'm sorry, that's where these are from. These were formed, this equivalent set was formed from V537, V601. V13 is where we got this arc. And the arc indicates inequality. So I have an arc whose origin is a reactant on the left-hand side and a product on the right-hand side. This really only works if it's uni-bi or bi-uni, as because that gives you the inequalities you want. So if I go from C10 to C160, I know that C10 should be less than C160. And so I also know that C154 should be less than C160. So I take an arc, here's where C154 is. I have an arc from its node, which is in this mass equivalent set. And the destination of the arc is actually the same node because C160 is on the right-hand side. And the way games works is it looks for a loop or a cycle in the graph, because a cycle is equivalent to this contradiction that the beginning, one node in the cycle has to be less than another node in the cycle. But if it's a cycle, that means that node or molecule has a mass less than its own mass, and that's the contradiction. So that's the essence of the way this mass equivalent set idea works. Now, this particular algorithm only works for cases where you have these uni-uni or uni-bi or bi-uni reactions. There's a more extensive algorithm that, again, Wusub is the author of this, that involves some interesting uses of linear algebra. And that really takes care of almost everything else that you'd want to do. And it doesn't really extend the time very much for running the algorithm. And you still get this capability to be able to isolate where the inconsistency arises. So that's this extended algorithm. I'm not going to go through the details there. So, and I mentioned MeMote. MeMote does the atomic mass analysis for mass balance analysis. It does a lot of other stuff too, which is very useful. So it does something called looking for blocked reactions. So a blocked reaction is a reaction that, based on the inputs that you have, where you are you have initial mass, or you have a fixed fixed species, something whose concentration doesn't vary. These particular reactions are not reachable. You can't get there. It's like a disconnected graph. So that's useful because obviously, if you're expecting that reaction to do something, then you need something more there, either other initial conditions or you have some missing reactions. there are, some other things like that with reaction networks that it does. It does not address kinetics, and errors in kinetics laws are really common. And so that's in part because what they're primarily focused on is more metabolic models that are focused on flux balance analysis, but the kinetics area needs some work. Okay, so this is the broad introduction to this, so what do we mean by testing? And then also, what do I mean, the static error checking. So let me pause here. That we're going to start into some of the computational stuff. The first part will be on taking advantage of the games algorithm. It's in a package called SBML lint. Lint is a term that's used for static error checking in software. And so this is like a lint of an SBML model. I'll get onto that in just a second, but for right now, I would like to see if there are questions.
There weren't any questions in the chat over the last bit. So.
Okay. All right. Fine. Okay. All right. So this next part, I'll tell you. Okay. So what we're going to do. I should have mentioned this at the start. I did make some small updates. Not so much to the slide decks. I'm going to tell you the slide decks we're going to use. So the next slide deck we're going to use is the static checking. I don't think I made any changes there, but definitely you should, if you haven't downloaded this one recently. I made changes about a couple hours ago, so you're definitely going to want to refresh
Currently
that
at 10:38.
Yeah, okay. Pacific time, right? So you definitely want to get a more recent copy of that one. And as before, I tried to make sure that the exercises were available to you separately, the answers to them, or at least the answer I went through. Okay, so let's go on to the static checking. And okay, get this out of the way. All right, so you're probably used to this by right now. Do a run all, make sure you got everything going. Oh, this is my, okay, so the usual thing as I organize my notebooks, the preliminary sort of sets up the environment for you. Tried to go through that on the first day to show you what's there so that and you're aware of, where things came from. I'm not gonna, for the purposes of this particular lecture, I'm not gonna review that again. And you just hide it because it's less helpful for you right now. All right, so it's mostly what it has to do is it does a pip install of Tellurium and a pip install of SBML lint, this static error checking codes. Okay. All right. So the first part of this that I wanted to just explore with you a little bit, not in great detail, is that in general, when you encounter a mass balance error, you can treat this in a couple of ways, and we saw this before. You can explicitly include the molecule. So like, I mean, this is basically that this is the same error we saw before where J0 includes the inorganic phosphate and J1 does not. And so clearly that's an error because it's inconsistently utilized. But you have two choices here. You could, explicitly include the inorganic phosphate, or you could choose not to include the inorganic phosphate. And clearly you're going to end up with, in terms of the actual simulation, the actual values that you see, it will look different because, this is a uni-bi reaction and the interpretation of the kinetic constant is different because now you've got, certainly an equilibrium constant with two products. Over here, you have, uni-uni reactions and there's one product. So obviously these things are going to look different. So you have to decide, what makes sense for your particular model. Both of them will be correct in terms of a stoichiometric inconsistency, or well, I'm not correct. Correct is not the right word. You will not detect a stoichiometric inconsistency. Whether it's correct or not is a bigger question. Atomic mass analysis would complain. Moiety analysis might complain too if you didn't specify what was implicit. So anyway, just to be aware of, you have many approaches to solving this. Okay.
So one other thing,
please.
Yeah, I mentioned this in the chat, but another option here is to use the second version with with phosphate, but to flag it as a boundary species so that it doesn't, it's not being used, it's not being like consumed or produced by the simulation, but you see it as far as like the moiety analysis would then flag it as correct.
Oh, okay. Yeah, yes, you're right. Yeah, that's yet another possibility, right? Yep. Yeah, that's it. And actually that would be sort of, oh, that's interesting. So really, yeah, that's actually a blend of the two, isn't it? Because this model makes it implicit. Essentially what you say by a boundary species, you mean something that has fixed concentration.
Right.
It does, its concentration does not change, which is what this model is saying. But, you know, essentially you would get the equilibrium values for ADP and ATP that look like this, right? Presumably, or close. Actually, I'm not sure that's true. Yeah, no, it probably should, because I'm not sure. It wouldn't. It actually would be a third result, because the P would always be a constant.
Right,
Yeah,
and it would be a non-zero constant. Like right
change.
in this model, you have P starting at 0, but if you actually have a lot of inorganic phosphate in your solution,
you pick a larger number.
Then
right.
basically,
yeah, and P goes up here depending on the. You get your P from ATP basically here, so it's going to be dependent. Actually, that's where it's going to be. Okay.
So if you have,
you're right. That's it. Yeah, the third option. Right. Okay. So this part here is going to be about actually using the SBML lint package, in particular the game's stoichiometric inconsistency checking algorithm. This is, you know, as long as you can get through that initial part of the notebook here, you know, running the preliminaries, install SBML lint, you should be able to do this relatively easily. This should work just fine. So the model up above, there are 3 models that I have up there. The first one, the ATP_1, I probably should have called it, or ATP1, is the one that's incorrect. That's where the phosphate is used inconsistently. And if you run, I can run this here. If I clear the output, so you actually can see that it's run. If I run this here, SBML, so lint is actually I should show you where that comes from. Let me show that, because that's from the SBML lint package. So if we look at the import there, I usually find it's easier to, you know, just import the particular tool you want. So that's where this comes from. So you should pip install SBML lint. That comes in right here, right there. And then the import is of this form. So there are some sub packages here, and the lint package is in this set of tools here, in that directory, SBML lint, all lowercase. So if we go down here, then look at the mass balance analysis. So, you know, this is what comes out, this sort of textual report, and shows you that inconsistency over there. Here is, you know, the kinds of things that you get then with the models if they do not have an error. So, you know, I think what would be good at this point, and I actually realize I have not done this, and I probably should have, is if we go back to the slide deck and we look at this right here. You know, I think a really good exercise for right now, and I haven't done this, so I'm hopefully it comes up with something reasonable, is try using SBML lint, that lint method, with this network. And to be able to do that, let's make this very explicit. So to be able to do that, what you're going to want to do is the arguments to the lint tool here is you just need this. You need the antimony string. So you're just going to create an antimony model for this. Actually, you know, I think I'll do. Well, let's see here. Can I'm afraid that this is actually. You know, I think I could
care
go
about
ahead and do
the
this
reaction rates, or does it not care about reaction
no,
rates?
it doesn't. It doesn't. We can put that in. Yeah, no.
Then all you should need to do is just copy this in as an antimony model and just add semicolons.
Right. Yeah, that's it. And
work.
actually, you know, I was thinking maybe I should do this, because that when I uploaded this to Google, to show you as a web page. It created, I think it created an image. And so you're not going to be able to get to the text. And that's going to be more painful for you. Let me see if I have the actual text over here. No, I don't. I thought I did. Okay, well, all right. So that's going to be the nature of the effort, is to, you know what? How about this? Let's do this together. And Lucian, if you could help me on this one, that would be awesome. So what I'm going to do is, let me go back to this over here. Yeah, exactly what I'd like is, so we're going to have another exercise here. Let me create another exercise here. We'll call this exercise part 1. And then let's see here, code. And then what I'm going to do here is we'll call this a model. And then, okay. All right, so here's going to be my, like doing it with a string. Okay, all right, so what are my reactions?
Right, we have V8, which is C10 plus C10 going to C11.
Okay, so, all right, all right.
V8 colon, whatever, yeah.
C10 plus C10?
Uh-huh.
Okay.
Goes to C11. And then you'll need a semicolon.
Yeah, and then I'll just say 1.
2, yeah. Sure.
Okay, and that's V8, and I think I did V star. Okay, all right, go ahead.
V13 then is C10 plus C154 going to C160.
Okay.
Then V208.
It's in the chat.
Oh, it's in the chat?
Oh, thank you. Someone was much faster.
Oh, so nice.
Oh,
Just
wonderful.
Copy and paste that in.
Copy and paste then. All right, let's see here. Yeah, thank you. Someone was really fast.
Nice.
All right. See if I can get here. There we go.
All right, you get an extra 10 points there. So
yeah, really. Yeah, we'll double your grade for the class. Yeah. All right. Okay, and the only thing I have to do is I have to add the kinetics here. That's no problem. Okay, so let's see if
you're gonna have to share your screen again, Joseph.
Oh, am I not sharing the screen?
Correct.
Okay, I'm not. Somehow I stopped sharing. Okay,
Somehow you stopped it. Accidentally clicked the button.
I don't know how that happened. All right, let's see here. Thank you for letting me know. That would be very inconvenient. Too many windows. Google Chrome. I think it's, yeah, this is it. Okay, can you see my screen?
Yes.
All right, good. All right. I always do this just to make sure that there are no syntax errors. Okay, so that loaded okay. All right, so what we're going to do is let's go back over here. And I think my experience is that almost all programming involves copy and paste of something that's pretty close to what you want. So we want, you know, that's a copy of this cell right here. Hopefully you saw that. And then I'm going to add a new cell down here. And I'm going to just say, look for stoichiometric inconsistencies. And I've forgotten which biomodels it is in bio. Okay, so here's what I've got. That was the original one. And let's put in model string and see what happens. Okay, so here's what it says. So let's see, you've got at least one error. So it says because V601 says that these are the same mass, C154 and C86. And then we get these are the same, C160 and C86. So that means 154 and 160 are the same mass. But here, 154 is less than 160. So that looks reasonable. That makes sense to folks? What happened there? And thank you again for the reaction network in the chat. All right, well, what I was going to suggest is, and this shouldn't take very long. Oh, there are a few others it found. Oh, that's interesting. Okay, so there are a couple of other errors in here too. Interesting. Okay, when you see pseudo something, this is using the extended algorithm. I didn't go into a lot of detail about what that is, but basically what the extended algorithm does is it treats these mass equivalent sets as actually new chemical species because they have the same mass. And then you'll see reactions, what are called pseudo reactions, because obviously it's not a real reaction, where we're relating a mass equivalent set, mass equivalent sets to one another. And it gives you, okay, so actually 2 errors it found there. So I guess what I'd suggest here is give you like 10 minutes. It probably won't even take that long to do the wolf model. And just a reminder that, let's see here, let me add that over here for wolf model. In wolf, wolf underscore model. Okay, so. Yeah. Now you should see it. Yeah. So this means, that's where the model is. Try running it, see what happens, see what you find. And then the next part of that is that you notice that in the, actually, let me print this out here. Probably makes sense. Yeah, let me actually print out the wolf model. Okay, so this is the wolf model. One thing that's sort of interesting here, going back to our old friend ATP and ADP, you see here, J9, ATP goes to ADP, this, we're ignoring the inorganic phosphate. Try putting it in, okay? So that's, part 1 is really simple. You're just, doing the error checking for the wolf model. Part 2 is to modify the wolf model and do this. And the way you're going to modify it is you can just, once you print it out here, you can copy it like this. And then for the second part over here, you can paste it. So now you have your own copy and you can, say like, new wolf model. I guess I should be consistent with my capitalization equals. Okay, this is not a string as it stands right now. We'll make it into a string. Okay, and I have to have an end quote down here. Okay, and now you've got the new wolf model, and then you can, modify it any way you want, and add in a phosphate, remove a phosphate, that type of thing. So I think let's do this where go ahead and do just the error checking on the new wolf model, and then I want to see, we'll see if there are any questions about that, and then spend a few more minutes on the second part. And I'll give you, let's do 20 minutes. So it's like going to be 35 past the hour. And to work on this for a little bit. And then we'll move over to the second part here, which is going to be dynamic, the dynamic testing, where we're actually going to do things that look more like a unit testing in software. Any questions at this point? Okay, all right, I'll see you in about 20 minutes. Okay, so here's what Lucy and I were talking about. So we made pointed to, for example, in the wolf model reaction J9, where we have ATP goes to ADP. And the thought is that what we could do here is if we wanted to explicitly include inorganic phosphate, I'll use
The wrong side.
I'm sorry.
ATP already has the phosphate.
Yeah, thank you. But that would have been caught.
That would have been caught, yeah.
That would have been caught. Okay, so if I do that, I mean, that's the change we're talking about. But this relationship between ATP and ADP and the presence of the inorganic phosphate, that occurs in several places. For example, up here, we see 2 ATP.
Oh, interesting.
Over here, going to 2 ADP. Well, we have to include over here we'd want to also include the plus
You know, before
2.
you do that, someone tried just adding it to J9 and then ran a check, and the check didn't find any errors.
Right, right. And that's interesting. So that's actually something else I was going to point out. It didn't find any errors because it's looking for inconsistencies, not correctness.
Well,
And so,
wouldn't that be, wouldn't you imagine that it would find it in reaction J1 there? Like if you
in
if you
reaction
only
J1
have it in
then?
J9, maybe you don't have it in J1.
Well, it doesn't know about the semantics. I mean, I think in your mind, you have the semantics that comes about because
No, just a mass balance thing, right? Again,
Oh,
if it knows, well, maybe it's because it's a by reaction and it
yeah, it's
doesn't
a
analyze by
it's more
reactions,
complicated, right?
so it can't do it.
I mean, there's another level of logic that can be applied to this, to go ahead and do that. But I think that's the reason why it's a limitation of the stoichiometric inconsistencies,
Okay.
what they can do. But if we
So
look for a reaction, go ahead.
No, is it like if you knew that glucose was equivalent to fructose 1,6-biphosphate, and then you knew that ATP wasn't equivalent to ADP, then J1 would be flagged
So
as
I mean, if there are a
inconsistent.
couple of other reactions in there, then it could figure it out. But there are limitations. So the point that Lucy and I were talking about before, if you look at a reaction J4, line 11 in my source over here, you see that ADP appears in the source, and ADP is a product, or ADP is a reactant, and ATP is a product. So you need the inorganic phosphate over here of ADP. But then if you also look at the kinetics over here, the kinetics, which I'm going to create a line break right here so you can see it all on one screen. Well, you can't even see it then, but the kinetics do involve all the reactants like ADP. So presumably you would want to include, this new reactant we added, the phosphate over there as well. And I think, and then I've got it over here too with the ADP, and I might, potentially I need to include it there as well. So those are the things that you'd have to think about a bit more beyond just changing the reaction itself. If you want the model to change, as Lucian pointed out, then you really, well, I mean, technically it will change the model because you're talking about, what transformations take place. This is the rate, what you're going to do is by adding the inorganic phosphate here, you're going to change the stoichiometry matrix. And then the kinetics expression is going to change the rate at which the reaction is actually occurring. And that will affect what the concentrations are for the species in both reactants and products. Anyway,
is there there's another issue here potentially that is, I wish I knew biology better. Are phosphates actually being attached to any of these molecules?
Oh,
just biologically,
yeah, that's more complicated. Yeah, now we're getting, and you're beyond my knowledge too, in terms of the, like our complex, a lot, usually with these kinds of models, we're talking about some pretty significant simplifications.
Right.
Like the assumption is that this is all in like one pot or something, but obviously we have enzymes involved here too. And the way catalysis actually takes place is more complex.
Yeah, like you have glyceraldehyde 3-phosphate and it goes to no, I guess it doesn't. But
okay.
Oh yeah, so glyceraldehyde 3-phosphate and it goes to just glycerol. I'm gonna guess that it lost a phosphate in there or something, right? Or something. So
it looks like it, right?
Like,
oh,
yes,
that's a good point. So that's a really good point.
So naively, just adding plus P everywhere you see an ADP is also
right.
wrong.
There may be more.
Yeah.
Yeah, absolutely. Yes, I would agree with you. It would seem that there may be more that needs to be done here if we want to actually consistently deal with the inorganic phosphates. Right. It's not just the ATP and ADP. Yep, that's a good point. And then again, what does that mean in terms of the kinetics as well? So there's a lot more there.
Right. Claire has a question about, she says, I was using lint on some personal models, ran into a situation where it marked an inconsistency or molecule is being transported with energy into a compartment and diffusing into that compartment. It was marking that energy is not being consumed in the diffusion reaction. Is that just a shortcoming of length, or should it be overwritten by our understanding of the model?
Oh, that's interesting. Yeah, Claire, could you send me the model? I'd be curious to take a look. Make sure I understand more completely what's going on there. Because I mean, this whole analysis is, makes the assumption that anything you put in the model has mass. And if you're talking about energy, I'm not too sure. I want to see how that actually fits into the model, because it may be that then the interpretation has to be different, because I don't know how to, it's not dealing with a mass energy equivalencies.
Yeah.
Right.
She's asked if you want to just email it.
Yeah, email is fine. You can do Joseph, Joseph .Hellerstein, HELLERSTEIN @gmail.
Another possibility there that might just fix it is to flag, actually it wouldn't work. I was going to say to flag the energy as a boundary species, but I think the linting thing may
yeah, you can specify. There's a way
part.
to specify something as and we use the term implicit species, that you don't try to mass balance. So that's another thing that you can do for energy. But let me take a look and see what she's got. Okay. Other questions? All right. So I'm going to go on to the third part. We have a bit over an hour. And the third part is this one here about the dynamic testing. So do the usual thing of running stuff. And let's see over here. This is one that you should have refreshed from this morning, because I made some modifications around 10:30. So with dynamic testing, the term dynamic comes about because now we're actually going to run simulations. And what we're trying to do is see if the simulation results make sense from the point of view of our expectations. So let's sort of set the stage here about what this means, because obviously we've constructed these models because we want to try and understand or discover relationships that we don't already know something about. Oh, I see that yes, okay, I see what I did wrong there. Apologize for the delay there. Okay, fine. I guess there may be a refresh for the refresh. If you run into an error when you've refreshed your model, I'll show you the mistake I made. Apparently I didn't check it. So back to that sort of framing what we're trying to do here. So obviously the whole purpose of running a model is to aid in discovery. And so, it's expected that you don't know many times what the outcomes of the model should be. So, does this sort of undermine the whole premise that, we're going to talk about dynamic testing and we're testing for the outcomes when we don't know what the outcomes should be? I mean, how do we get out of this quandary? And the answer to this is, again, sort of drawing from the experience from software engineering, is that, you don't always know what the output of a function will be, but that certain relationships should hold. If, for example, you had a function that sorted, some words alphabetically, you have some expectation that, whatever the list of words that came in, the length of that list should be the same length of what comes out. And those are what are called predicates. And this is actually sort of the foundation of software testing going back, pretty much like half a decade, is that you want to figure out for each unit that you're testing, and that's really what we're working on here, kind of unit testing, what are predicates that should always hold? And therefore I can test using additional software to run those same codes, those units, and ensure that the predicates hold. So that's sort of the starting point is, although I clearly do not know what the outcomes of the simulation should be in any specifics, but I may know something about some predicates that I do want to make sure, are enforced. So that's sort of an abstract statement. Let's go through and work through in a specific example and see what makes sense in terms of this idea of a predicate. So we're going to look at this model here where we have 3 species. It's a linear pathway. So we have S1 goes to S2 to S3. Oh, let me just do a check. My screen, you can see my screen, Lucian?
We can see your screen. What was the question?
Yeah, you can see my screen. I just want to make sure that
Yes.
its screen is visible. Okay, great. I have gone on for long periods with nobody saying anything and my screen was not visible. I just want to make sure it's visible. Okay, great. Thank you very much. So we've got this linear pathway with 3 species. S1 goes to S2, goes to S3. We're going to, there's no fixed species. It's, we don't have something that's driving S1. Instead, what we're going to do is we're going to have an initial amount of S1, and that as the reaction proceeds, then all the mass is going to be in S3 because it's all going to get transformed to S3. So what can we say about the time course and the values of S1, S2, and S3? Well, one thing is we expect that S1 over time is going to decrease because its mass keeps on getting transformed into S2 and S2 into S3. And secondly, we expect that S3, its mass, the mass for S3 is going to increase because it's essentially the sink for everything that's happening. And for S2, what do we expect to happen? And S2 is a little bit trickier. With S2, we sort of expect that, things are going to initially rise up, as we are transforming, as we have a lot of S1, but after a period of time, it's going to drop down. So it's going to rise and fall. And so this is summarized in terms of these 3 statements over here. And as you can tell, I mean, this is a very simple pathway, a very simple kind of system. So you say, okay, fine, that's not too hard to figure out. In a more complicated situation, different, but you might very well, and you sort of explore this a little bit with the Wolf model as the exercise, you might very well have something where that, for example, Wolf model, remember, deals with glycolysis. You might say that, gee, I start with glucose and end up with pyruvate. So, I sort of expect to end up with a lot of pyruvate because it's 3 carbons and glucose is 6 carbons. So, sort of expect that, I end up with a lot more pyruvate. Also, it's the end of the pathway. So I might argue that over time, the amount of the concentration of pyruvate is going to, over time become larger than the amount of glucose. So that would be an example of an expectation. So these are the kinds of predicates or expectations that you're looking for in order to test that the model is doing something reasonable. And the thought is, and the way this becomes useful, and we will do a certain amount of work to be able to test for these predicates, and it doesn't come automatically, much like I gave the example with software unit tests. I mean, typically, if you're writing a software package, you're going to write as much test code as you write function code, code that actually does what you want it to do. Well, similarly here, we're going to write, some test code, and, it's going to add to, what it takes to actually, produce the model because we're writing more stuff, doing more stuff. So this is not a one-shot thing. You don't want to just use these tests one time. I ran the model and, it's consistent with my expectation. The idea is that a model is an iterative kind of work product. You have an initial idea, you try it, you see the results, and then you modify it, you get some laboratory data, you modify it, and so on. What we're looking for are predicates that throughout this process that we're working on, we expect these predicates to hold. And therefore, as we modify the model, extend the model, it is so easy to make mistakes. We want to make sure that these predicates always hold so that we have some assurance that we haven't done something silly along the way and our output is really meaningless. So let's go through, here's an example for this linear pathway. So here's the model. I call it an incorrect model because it has an error in it. Who sees what the error is in this model? Anybody have some thoughts? I look in the chat. Oh, yeah, thank you.
Second one should be multiplied.
Yes, thank you very much. Exactly. Good catch. All right, so, oh, I even modified. Yeah, right. Yeah, it's right here. That's what the error is. So this is a very easy typographical error to make. This is intended to be mass action kinetics. I used the wrong chemical species. It should have been the reactant over here. And instead I used something from a different chemical expression. So as a result, what happens here is I sort of get the right outcome for S1. Its mass gets transferred over to, it declines, and S3, but S2, it's always 0. So what's going on here? Why is it that happen? And it's because I have the wrong chemical species right there. So if I fix that, then I sort of get the effect that I was after. So I'll go back to this one with the incorrect one. So we have that for our reference later on. All right, so, and here's the correct model. Okay, so you can see that again. All right, so at this point, we have these, for this model, we have an example of, an error that we could have made. That's, that type of typographical error is very easy to make. And, for 3 species, linear pathway, mass action kinetics, you'll find it right away. But, throw in, 10 species and, 20 reactions and, you've got enzyme kinetics and, more complex feedbacks. It's going to be a challenge to figure out where your typographical error is. So, and it's in the kinetics. It's not something that's logically wrong. It's just that you get the wrong answer. So given that we have sort of these expected outcomes, then how do we incorporate this into a kind of software that will actually check for these expected outcomes? I mean, I can look at this and say, this is wrong, this is right. I could do that, but that gets to be very cumbersome if I'm doing, if I have a lot of different conditions that I'm looking at, and I expect these predicates always to hold. I don't want to have to do this manually. I want to be able to do it automatically. And that's in fact what, most software packages do. They have something called continuous integration, where they run the tests all the time. Every time you make a change to your code base, these tests run and they give you a report if they fail. But that's the kind of
a little bit about that this morning, where I showed them some examples of that happening. With
great.
And stuff.
Yeah, no, that's great. And that's very important. That's one of the reasons why people are able to build software with literally, tens of millions of lines of code, is because they have this kind of integrity checks. And so if we expect to be able to build big models, chances are we're going to need integrity checks too. So how do we go about this? Well, the approach I'm going to suggest here is actually drawn very much from the experience in the software industry and this idea of unit testing. And basically what we're going to do is we're going to put into code the these tests that we just had before. So for example, remember up here, we had 3 outcomes that we were interested in. So S1 decreases monotonically, S2 increases monotonically, and S2 it initially peaks and then declines. I guess I don't know how to spell declines. Okay, it's probably not necessary for you to reload, refresh, just to correct my spelling error, but okay. Okay, S2 and then declines, and S3 increases monotonically to 0. So the first challenge is then, how do we translate this into something, something that we can use in a program? So what we want to do here is, so we're going to, here's sort of the setup. We're going to run the simulation for the model, because we're assuming we have the model and we've got everything set in the way we expect it to be in terms of initial conditions and kinetic constants. All that is all set up. We're going to run the model, and then we're going to run some, we're going to take that output. So when you run when we run the model here, for example, we produce this data. That's the result of the simulation. Data is going to be the input to a separate set of codes that are going to look at data in light of these expectations over here, we've set over here, and say, do these data match these expectations? So remember what comes out of the simulations here. I'll show you here. If we look at data, so you see what we're actually dealing with. If we look at the data over here, this is what's called a named array. And the named array actually includes information about what the columns are. So it's a matrix, essentially. First column is always time. And then what we're getting out here are the species. And these are concentrations because they're in the square brackets. So what we want is really some additional codes that can pick out these values over here and then use these as input. So this is this S1 here, that second column. If I say data of all rows and the first and column, it's when I say 1, it's actually 2 because Python counts from 0. So 0, 1, that's the column over there. That's going to be this is like 10, 9.0, 8.1, that type of thing. Yeah, so this is 10. It's the exponential over there, 9.0, 8.1. So I can get this vector very easily. And what I want to do is check this property on the vector. Is S1, that vector, does it decrease monotonically from 10 to 0? That's what I want to check for. So we need code that's going to do that. We have to write that because that's a test we need to provide. And similarly, if, you know, for S3, we'll do the same thing, but we're looking for increase rather than decrease. Now, you know, there's sort of a neat trick here. Actually, checking for an increase is the same thing for checking for the negative of a decrease. You know, so if I make these guys all negative, then they should be decreasing. So we actually only have to write one function because, you know, we can easily check this if we check that. This one's a little trickier because we have to have something that rises up and goes down. And we want to make sure that, you know, it doesn't rise up, go down and go up again. You know, we don't want that. So that one's potentially a little bit trickier, but that's the code. That's our first step. We have to be able to express these tests over here for the 3 chemical species. So let's talk about that. That's this right here, testing expected outcomes. So here's the first function, is monotone. So what is monotone does is it takes in an array of values. So, you know, like what I just showed you up here, we take in data like this. This is S1. And the other thing it takes in as an argument is the direction. So if direction is a positive one, it's increasing. And if it's a negative one, it's decreasing. And this is one of those keyword arguments where by default, it's just checking for increasing. But if you say direction equals -1, it'll check for decreasing. And so the way this works is it makes sure that, you know, you could provide this, you know, a little more detail. This typically is going to be an array, but if it was something else, it makes it an array. That's what line 15 does. Then it computes the difference between, you know, successive values, and this takes care of the negation part, you know, whether it's increasing or decreasing. So, and the trick here is this is all about slicing. So this says take the second value in the series and subtract from it the first one, and so on down. So we're computing a successive difference. So if it's increasing, we know that all these values would be greater than 0. If it's decreasing, all these values should be less than 0. But if it's decreasing, we would have multiplied by, we would have said a -1 direction. So that, again, will make it so that it's all increasing. Now that's the way this particular piece of code works.
Aren't those indexes reversed? You have 1 colon
Which
and then
ones?
you have colon -1.
Oh, okay. So colon -1 goes from the first element to the second, to the one before the last.
Okay.
Right. So what I'm doing is I'm saying,
okay.
yeah, that's
one through the
yeah.
end.
I'm glad you asked that question,
Okay, yeah.
Lucian, because I'm sure others would have been confused about it.
Okay.
Yeah. Right. This is actually saying this would take, you know, whatever the second one is and subtract from it the first, and then so on down.
Got it. So it's so
Okay.
those arrays are all one less, have one less element. than
Well,
the
all
original
one
array.
less. Exactly. They're of the same
Okay.
size. Yeah, if they're right. That could be a problem if they're not of the same size. Right. So what I try to do with all of my code is make sure that I've documented what it does and what the inputs are. So values and directions. So values would be an array. Actually, I should say or list because I convert it to an array. And direction is, I say it's a float. I don't know why I say it's a float. It should be an int. And it's either a 1 or -1. And 1 means increasing and -1 means decreasing. I mean, actually, it could be, you know, as long as you say, actually, it could be just as long as you use a negative number for decreasing, for the direction being going monotonically, monotonically decreasing, and a positive number for monotonically increasing, it will work because it's just looking to make sure that the signs are right. And then the other thing I always include are tests of various situations. So this is if it's, you know, if you have an increasing value, and then make sure that this doesn't work, you know, that should not be monotone, this should be. What I'm going to do is, let me just go down here and show you some examples of this. So I find this kind of thing sort of useful. Let me just get rid of the output for right now. I find this kind of thing is sort of useful, is to test it in various ways. So we're going to analyze these various series here. So this one is clearly an increasing one. 1, 2, 3, 4. This one is clearly decreasing. This one is, you know, increases a little and then decreases. So let's see what happens when we run this. So, and it checks to see, it goes through and does each one of these checks. So it says, is it monotone increasing? Is it monotone decreasing? Or is it the concave we'll get to in just a second. But you can see that 1, 2, 3, 4 is increasing and it's not decreasing. And 4, 3, 2, 1 is not decreasing, it is increasing. And 1, 4, 3, 2 is neither increasing nor decreasing. That gives you a feeling for it. Okay, any questions on the is monotone about how this works? Check the chat, see if you have any comments. What does assert do? Assert, okay, the argument of assert is something that's a Boolean, something that's either true or false. So is monotone returns a Boolean. It returns either true or false. So it makes sure you have to have all of them are greater than 0. That's what the all means there. So this is going to return something that's either true or false. Assert, if it's true, does nothing. If it's false, and let's actually show you as an example over here. Assert if it is false. So if I just say assert true, that does nothing. It just, you know, just stays there. If I say assert false, so if I had a function that returned false, it gives me an error. It just says assertion error. And that way I know whether or not, basically what I'm doing is I'm trying to make sure I don't make a mistake in these codes over here by always running them and having various tests. So I've documented what it is, and then I test them to make sure they work as I expect. Other questions in the chat? Let's see.
Asserts will also stop the execution of the code. So if you have,
yes, it will.
As you're running, as your Python script is running, if it hits an assert and it fails, it won't try to do things after that. It'll say like, no, something's wrong here. You need to fix that before I do anything else.
And which is extremely useful because it's easier to find to fix a bug if you get the error closer to the source of the bug. Once you know you've returned a wrong result, and then other things go wrong, and other things go wrong, and other things go wrong, it's very hard to unwind all of that. So that's another reason for having an assert. Okay, so that's is monotone. So let's go on to is concave. Now, to translate this into code, there's actually an interesting trick here when you think about it. Let's go back to what the curve looks like. So the trick is that if it's concave, what you're saying is that there's an initial part that increases and then the rest of it decreases. That's what you mean by is concave. So if you could find this point, sort of this peak over here, then you could say, gee, if I'm once I know this peak, I know that everything before the peak has to be increasing and everything after the peak has to be decreasing. So that's sort of the strategy with this. Now, obviously, we don't know the peak, right? That's not given to us. But what we can do is we can search across all of the values in the array that we're presented with and say, basically, is this the peak? If this is the peak, I should have, the first part is increasing, the second part is decreasing. But if I can't find any peak like that, then it fails. And that's really the way this works. So if we go to, let's go down here and take a look at these guys over here. So actually, I guess I don't have one. Let's give an example with two. Okay, so you can see that 1, 4, 3, 2 is something that should be concave because it increases and then it starts to decrease. So you see that down here, that will be concave, and these other two are not. But let's construct a more elaborate example. Suppose we had something where we had our values were equal to, say, 1, 2, 4, 5. And then we'll go down, we'll go 3, 2, and then we'll go up again 6, 7, 8, 9. Suppose we had something like that. I mean, that clearly it goes up and down. It goes, increases there to 5, decreases to 2, increases to 9 again. So it sort of goes up and down like that. Now that is not something that should be concave. So now if we say is concave of values, let's see what happens. So that's not. Now, if we did this a little bit differently, if I took out these two guys, let's see, well, that's not going to be enough to take out. Well, let's do this. Okay, so this is all increasing. And then let's say I go down 5, 4, 1. If I run this, that should be concave. So hopefully that makes sense about how we're doing it. Taking advantage of that fact of, can we find that sort of peak point? If we can find the peak point, then we've got it as concave. Okay, so this is the first part. Whatever you choose as your tests that you want to look for, you have to be able to express it as in code, as a function typically. And once you've got that, then we're going to go through and take advantage of something which is part of Python broadly, or the ecosystem, the packages that are available. There's a package, much like Tellurium is a package and NumPy is a package. There's actually a package just for unit testing called Unit Test. That's this right here. And we're going to take advantage of that package. And then I'll show you sort of there's a template for being able to run these tests, and you'll take advantage of this template to do it. Gosh, I've sort of made this a little bit. Okay, I sort of combined some steps together here, but let's see. I'm going to, to make this a little bit easier, because this makes it reusable, but it also hides some things. And so, or takes it a little bit step further. Let me show you how this gets written so that it makes more sense. You can see the steps along the way. And so this generalization of it is not as required here. So I'm going to take out this. I had made it into a function so that I could reuse it in various ways. And I'm going to take out the function part of it. You can see it being done in a simpler, more compact way, or, it only works for one shot, but that's okay. All right, so, and then let's see, we're going to, the one we're going to test, let's test the, and we'll start out by, actually, I'd rather test the incorrect model. We have the incorrect model over here. Yeah, let's test the incorrect model. I want to show you what happens when it fails. Okay, so here we've got over here, there we go. Okay, now let me take you through it. Now I can show you and I guess I truncated part of this. This has to import. Okay, so this brings in this package, the unit test package. And what we're going to do is take advantage of that package to be able to test the model. Then there's some standard code you just put in, and I can tell you the details behind it, but it involves a little bit of knowledge of object-oriented programming. You don't need to know that, just it's sort of a template. So you put in this statement here in line 6. Just you can do that as is. And then you'll also put in this stuff down here. I can tell you what it's doing in loose terms. This defines a kind of structure in Python called a class. If you're familiar with object-oriented programming, it's sort of a template for creating certain kinds of data structures. Down here, what's going on is much like what you've seen with using Tellurium, where te.load_a, and then you give your model. That's a similar kind of thing that's going on over here. You're loading the this class, that test model, and this is where you're actually running it. And so you're going to run all the tests. Okay, so but that's template stuff. You can just copy paste. The parts that you're going to care about are this. So there is one function here. These are all functions. Technically, they're called methods because they're within a class, but it's really a function. You want to define it just like this, where it says defines, and it matters that this is an uppercase U there. That actually matters because this test class will check for that. And the self is important too. So you can get all that done. Self is actually a variable that's used internally. And so what you're going to do is you're going to load the model that you're going to test. In this case, we're testing the incorrect model. And you're going to put that into a Roadrunner object. By saying self.roadrunner, what it does is it makes this data available to other functions. That's why you're doing it. Then you can run the model. And so here I'm putting the output of the model. So I'm going to run self.roadrunner because that's where I put the Roadrunner. I'm going to simulate over some range. And then I put the results over here. So this setup is run before each test. So each test gets it, and this is so that, if it turns out that a test modifies the data, you're making sure that another test will get clean data. And then what we have is we have tests for each species, or really, it probably would be better to say for each outcome that we're interested in, but it's organized here by species. So for S1, species 1, we expect that to be monotone increasing. So what we have over here is we're invoking that function that we wrote just previously in the previous section, is monotone, and we're looking at the data that got produced by running Roadrunner, and we're looking at, since we can pick out that array by saying S1 in brackets, and the direction is going to be -1 because that should be decreasing. So we're asking, is this monotone decreasing? This will return, if this returns true, then assert true is true. And this is very much like the assert you saw before, but this is the assert that's used in the form of assert, that is self.assert true. That's the form that's used in unit tests. So we're using that infrastructure. So that will, and if this fails, we'll see an error report. Similarly here, we check for concave with S2, and then monotone increasing with a direction there.
Joe, I'm going to assume that these assert true things don't, like if they fail, they don't just stop then and don't run any of the other tests.
That is correct. And that's the reason for doing this. So
right.
The way this test infrastructure works is that it runs each one of these tests separately. And if it fails, that's not a problem. It goes on to the next one. It handles those kinds of failures. And that's the reason for doing this instead of the straight assert that we talked about before, because that would stop things. This way you find all the errors at once instead of sort of piecemeal. Other questions? Let me pause for a second because I was talking for a long time. Let me see if there's anything, nothing in chat. Anything else that someone wants to vocalize? Okay, all right, so let's run this. A lot of build up to run this. Okay, so here's the kind of output that you get. So this failed. So you get a dot for each test that you run. And I believe the dots occur in sequence, so I'm not absolutely positive. Sometimes it's sort of strange, but I think it's in the sequence in which they appear in your test code. So I see the first one ran okay, the second one failed, the third one ran okay. And then it gives you the details about where it failed. So it says it failed on line 16 in test S2. So line 16, here we are in test S2, this is where it failed. And it said false is not true. So this returned false. And the reason why it returned false is this is the model where we had the incorrect kinetics and we do not have S2 remain 0 throughout. And since we had our is concave test here, we discovered that S2 did not behave according to our expectations. So we can change this, check a different model. So correct model, we could do that. And now try running it. It runs okay. We detect no error and we see the 3 dots there. So what I was doing down here, let me just explain what it is I was doing down here. This involves, it's very common when you're doing, you're going through and sort of repeatedly developing models and evaluating models that you don't want to have to write the same code over and over again. And you saw here, what I was having to do is, as I was looking at these different models, I had to modify part of this, and that's a little bit inconvenient. Another thing that you can do is encapsulate all of this. So basically this entire thing here, encapsulate all that in a function. And so I created a function over here called test model. It has the argument, the model is the antimony string of the model. And so instead of, the load A over here where I type in the actual model name, what I do is I use the argument that was being passed there. And so now to test the correct model, I just use that argument. I just use it in this form, test model, and I could do it over here. I could do this with other models. So this, gives that same result that there's a failure there. So that's what was going on there to try and encapsulate that a little bit more. All right. So let me pause to see if there are any questions on this, because the next step is going to be to develop some tests for the wolf model. So maybe that prospect has gotten people interested. I see a lot of stuff in chat now. Let's see here.
Yeah, in general, like just why use unit tests instead of just rolling your own stuff? And so there are
right. So that's sort of
few options. Yeah.
Right. And yeah, right. You could certainly roll your own. Unit test provides a convenient way to get a lot of different features, especially when you develop many tests. So you can run them in batch. There's this opportunity for using continuous integration. You can do this with other things, but unit tests provide you, sort of with a standard form to start with.
I would say in general also that
Python,
the way Python is structured with its packages, that if there is a package out there that does some of what you want, just use it. It's probably going to be, as long as it's somewhat maintained, it'll be there for the life of your project, and then you don't have to worry about it. It's in general the reason to use libraries in your programming like overall. Like it's the same reason you would use Tellurium. You can write your own ODE models, but this is a lot faster because we've already handled a lot of the difficulty for you.
Right. Yes. Okay. So in this exercise, and I'll do the same thing with helping you get started. So we're going to do the wolf model again, and remember, it's the wolf model you can access if you do just wolf_model. This gets you the model, and we talked about that before. Okay, so that's just right, wolf_model. That gets you the antimony model. So what we're going to look at here is to help you sort of think through all phases of what's involved with testing. It's not just writing the code, it's also figuring out what expectations are reasonable expectations. so that you can then develop tests that are meaningful tests. So a great way to start this, and so let's put this in context. I mean, the Wolf model has been published. It was published 20 years ago, so why do I need tests at this point? I mean, that's a reasonable question to ask. And it may be that you want to use the Wolf model as the basis of something that you're developing that's more extensive. You're doing something with liver metabolism and muscle metabolism, and they're going to have some slight variations in some of the the glycolysis that's going on. Could be lots of different things. You want to combine it with the pentose phosphate pathway, a lot of different things that you might want to do, but there are certain characteristics that you want to make sure get maintained as you evolve the model and sort of the chemical context in which reactions are taking place. So a great starting point is then to let's just take a look at the data for the Wolf model itself. If we run the simulation and we say TE load a Wolf model, and then do the usual thing of and I learned from Lucien yesterday, I can actually say rr.plot, and that will actually do the right thing. Okay. Hey, Lucien, is there a way I can move this? I've actually been sort of rolling my own thing with MATLAB so that
someone else had a problem with that also. And we were trying to find a way to get rid of that. And the answer is no, we couldn't find an easy way to get rid of the legend.
I think isn't there an option to switch the legend off or not?
Veronica found an option in Tellurium.plot, but not in the model.plot.
Let's have a look.
You can also change it by the figure size.
Oh yeah, that was.
Oh well, that's it. Yeah, right. Okay, so could I as figure size, fixed size?
Hey, look,
it's fixed size.
I could do this.
Yeah.
Try it. Yeah.
Yeah.
Okay.
Work.
Yeah. I mean that helps.
Okay.
That helps a lot. Okay. Cool. All right. So
you can turn the legend off too.
Okay. Yeah. No, I want the legend because I need to know what's what. Yeah, but so it's a little bit hard to see, but I think that pyruvate is actually the upper one here. And then I think this is fructose 6-phosphate, and glucose is somewhere down below. It's blue, probably around in here. So there are a lot of different things that we might think about in terms of, what are the tests we want to maintain here. So for the exercise here, I encourage you to think about that as well. Is what would you like to test for as you put this model in, as you modify the model maybe a little bit? Maybe we're going to, for example, we talked about before, explicitly include the inorganic phosphate. We've decided that's important. Or another thing is I mentioned, combining it in very different, biological contexts with other pathways that are taking place. So one thing that we might say is, well, gee, we really expect that the concentration of pyruvate is going to be larger than glucose. If that's not the case, then, we feel like there's something that's wrong. We don't have it right. Or you might do something, with other metabolites that are present here. Look at their relationship in terms of the magnitudes. So that's one possibility. Another possibility is this model is all about oscillations. So, maybe we want to make sure that we preserve the oscillations as we modify the model, that's important. That's important. If we don't do that, then somehow we have, strayed from the biology that we were hoping to study. So that's another possibility.
That was exactly what I had to look for. I had the Wolf model, and I had checked it in over the course of changing it, and at one point I killed the oscillation, and then I had them find where I killed it.
Cool.
So this is exactly like, how could we have prevented this situation is by writing a test like this, and then when the first time I made the mistake, it would have notified me.
Okay, that's excellent. Now when Herbert and I have taught we teach a computational biology class, we go through some detail. We actually do the example of the looking to make sure that the oscillations are present. I leave that as sort of like a third exercise through. The reason why I don't is it requires a little bit more mathematic and computational work because you have to use a way of detecting oscillations. Most likely, what I recommend is the fast Fourier transform. So rather than getting that detour as part of this effort, because this is really about the testing, the dynamic testing, I'm going to use a simpler one, and that is this relationship between the magnitudes of the different metabolites. So that's what I sort of suggest down here. What is, take a look at some of the metabolites, figure out, are there ordinal relationships, then construct tests. Now you're looking at tests, this is different tests than before, because before we're talking about shapes of curves, and that's a property of a single array that, would reflect its shape. Like, is it increasing, decreasing? Is it concave? That type of thing. Now we're talking about the relationship between two curves. And so you have to, figure out, how you write that type of test. And then actually then pull this together into the test infrastructure like we have up here. So I'm going to let you work on this for about 20 minutes, because I think that's long enough so that, if you want to try and get to the point where you may not have necessarily solved it all, especially if this is, you're early on in your Python careers. But I think you will have gotten to the point where you figured out what's blocking you, and you can ask good questions. And we'll use the remainder of the time to answer those questions. So I will see you at 1:45. Let me see if there are any other questions before I see two things in chat. Anything else before we get started? Yeah, you could use eigenvalues too. I mean, that's actually an interesting one about the eigenvalues. We've had a lot of discussions about this, Eduardo. Yes, you could. It's a little bit of a tricky business because these are nonlinear systems, and the check for sustained oscillations is actually a boundary condition on the linearization. And so you're not 100% assured that you're going to get this right just by finding complex eigenvalues. You actually can get oscillations anyway, or not have oscillations when you think you do because of the boundary condition. But the thought is a great one. Okay, any other questions? All right. Okay, great. Cool. Okay, I will see you in 20 minutes. And we'll stop this screen at this. So I'm going to start by looking at the notebook that contains the answers to the exercises here. So this is a little different notebook than the one we were looking at before. Here it is. Right here. So this is the one, this should be in your folder, verification and validation exercises. And of course, you'll have to do the usual thing of, running at the beginning to get the virtual machine started up. So if we look at this, now the first question was about the relationship between concentrations. And we're looking at glucose, fructose, 1,6-bisphosphate, pyruvate. The initial interpretation is that, pyruvate should, we would expect pyruvate to be much larger than glucose, and that's reasonable. But if you look at fructose, 1,6-bisphosphate, its relationship is, with pyruvate in the simulation is actually more complicated. But there are a few cases where the pyruvate concentration actually drops below the fructose 1,6-bisphosphate concentration. So that if your test for, is greater than, the pyruvate is greater than the 1,6-bisphosphate, if you're looking for across all points in the time course, it's not going to be true for all points in the time course. Now, if you're just comparing pyruvate with glucose, you're going to be okay. But if you're comparing, go ahead.
Just a couple quick questions. One, someone wanted to know how to make a data frame because they wanted to use WolfDF, and if they change the model, then WolfDF would change also. And then,
okay, fine. Yeah. Yes, go ahead.
And then my other question is, just looking at this looks like a stochastic simulation. Is that true?
No, it's not stochastic. I'm just using, all I'm doing is I'm
Just playing a lot
picking
of
up,
points.
what did I do here? Like, oh, you know what? I apologize. Yes, I am looking, yes, I apologize. What we're
Okay.
looking at here is actually something that with the errors introduced. This is not just from the simulation. I apologize.
Ah, okay.
Yes. Yeah, no, okay. So I wanted to make the point that you may have situations where that wouldn't happen. Let me do two things here. First of all, to make this less confusing, I think this, no, that's not actually going to work like that. Let's see.
You could probably just like create it again real quick. But
Yeah, I think that's the easiest way to do it. Let me create it, and let's see. What did I have? I thought I already had it, but that's okay. We can just recreate it. We can do the Roadrunner is going to be. I think I had different time ranges, but that's okay. It doesn't really matter.
you should probably put at least a few more points. Earlier it was a little janky, so like you could still do 0 to. It looks like it goes from 0 to 5, but with more points collected. 0, 5.
Okay, so let's
200
do
or something. I don't know.
Yeah, okay, that sounds good. And then, okay, actually, what I'll do is let me use this as an opportunity to create a data frame too.
Right. That would be great.
Let's do both at once. Okay, so let's take a look at what we've got here. This is, let's look at what data. Now remember, data is this thing called a named array, and a named array has column names. So here are our column names, and then, but the content is a NumPy array. So to create a data frame, you need two things. You need the data, which is the array there, and you need the names. So we've got the names, and the names actually in a named array are in something called column name. It's a property of the named array. So if I look at that, column names,
Yeah.
that's what it's called. Yeah, there we go. So those are the actual names of the columns. So what I can do to create a data frame, it's actually pretty straightforward. I believe this is going to work. I'll say data frame, and then, first of all, you have to have the pandas package. So you say import pandas as df is the common, or PD, I'm sorry. This is the common way abbreviation people will use for pandas. And then within pandas, there's something called a data frame, and that's what we're going to make it use of. So I'm going to call this, I'll do lowercase wolf df, distinguish it from the observational data, the synthetic observational data. And you type in pd.dataframe. So PD to get the pandas package, data frame, get the data frame. And then I just put in data over here. So I'm just picking up the named array from before. So I can take a look at that. And then if I, let's look at, see what this thing is. Okay, so this is, a table like what we had, but like what we want. And so that is good. Let's see which makes sense here. So the first column here should be time. Yeah, and time goes to 5. And there are 200 rows because we specified a simulation. So the last time is 5, and there are 200 rows because we said 200 points. So all that is goodness. This is going to be time, and then the rest of these are the other columns from the array. So what we need now is to put the names in. And to do that, data frames have a property called columns, which you can assign. So then I can say wolf df dot col names equals columns. And now if I put in wolf df after that, yep, I think I spelled it right.
You want data.col names.
Okay.
Data
yeah,
call names. So, yeah.
Oh, yeah. Right, exactly. I've got the wrong one. I want data. I'm sorry. Data is what came out of the simulation. That's where call names is. Okay, right. My bad.
It's wolf.
And then I've got to spell wolf. Right. It needs a no. Okay, and there we go. So now we've created the data frame. It has this nice format over here. And now I'll replace what I had before here, which was the wrong one. Wolf df, that was the one with the okay, I have to type in all this df. This
Or
is the
just
one
copy it
with
from it, yeah.
all the error stochastics in it to introduce some error modeling. I wanted to make the point that if you have, sometimes your data will overlap and will not be 100% as you expect. And this will not work because the names that we're using actually have the concentration things around them. So you actually have to use the same strings. And so it has to have those square brackets around it because that's the string that's present in the column name. And when you reference it like this, it's got to look exactly like that column name. Time does not have that. So I guess I'm okay. We'll see. All right. So there we go. That's what it should look like. So these are non-overlapping and you can do the comparison as you would expect. So that should be fine. What I showed you down here below with the tests actually included the possibility that something might be true only a fraction of the time. That's what this is. You don't need it if you use the simulation output, which is what you should be using for a test. The simulation output. I was just showing that, if you had to generalize it, that's what you could do.
You might actually be simulating stochastically, though. Actually, we haven't
true
done that
too.
yet, but that is definitely a thing that you can.
Right, and that's perfectly fair, and absolutely, you could be simulating stochastically, in which case, that's a whole other story. Okay, so then here's how I structured. So once we have this test here is larger. And it takes a series. A series is what you get when you take a slice out of a data frame. So this slice out of the data frame here, if I say I just want the glucose column, that's what's called a series. The entire thing is a data frame and each one of these columns is a series. So is larger, the way I wrote it, it takes up one of those slices or a series and does its comparisons on that. And then here's the actual unit test itself. What the unit test does, now let's actually use the one we just created, Wolf DF. So that's the one where it's actually simulation output. And I said start index equals 400 because I wanted to get past the initial transient. Probably could even do it earlier. Let's do 200, what the heck? Let's see if it fails. Okay, and then that's my data frame, okay. And then, okay, so the other thing I have to fix here is, of course, these names are going to be expecting the square brackets. So you got to make sure your square brackets are in there. So that's the names over there. And there are easy ways to make it so that you don't need the square brackets. But I just have sort of save on time for right now. Don't include that little programming detail. Okay, and so what each one of these tests is doing. Yep. Square brackets, and another square bracket, and the last square bracket. And let's get rid of this line over here because that may be confusing. It's just it's commented out some old code. Okay. All right, so so this should run the test. Let's see what happens here. So each one is a test for is larger than. So pyruvate should be larger than glucose. Fructose 1,6 bisphosphate larger than glucose, and pyruvate is larger than 1,6 bisphosphate. Obviously, by transitivity, you don't need 3 tests. You only need 2 tests, but just for completeness here, I included all 3. So let's see what happens. We got an error. Okay, this is great. Let's see what our error is. I don't know what mistake I made. It was not intentional, but it's always good to have this as an example. Okay, so it looks like all 3 tests errored. They all failed in is larger on line 17. And they all failed because of this here, the length of the series. Apparently this is 0 is what it looks like, division by 0. Okay, so what did I do wrong? I wonder if
There were exactly 200 points, right?
Yeah, they're
so your start
exactly
index
200.
was the
Oh,
end of the,
yes, you're right. Of course, it's not going to work. All right.
Because earlier
So,
for your stochastic data, you probably had like 1,000 points.
All right.
Right.
So
yeah.
that's great. So so let's do the first 50 points. Ignore those and see what happens. Now it works much better. Okay, well, thank you, Lucy, and you saved me the. Nice to have someone look over my shoulder. I definitely have to pair program with you. It'll save me a lot
That's
of
right.
time. Okay. All right, so that's what we had there. Let's see how we doing on time. Okay, so we're really at time right now. Let me stop here. I mean, the last part here was about the frequency tests. We talked a little bit about that before. Do we have, I see a couple things in chat. What have we got in chat? Okay, yeah, thank you. Someone caught my error with the wolf. Thank you. Oh,
the other
okay.
question was
So if we
earlier on,
make
just how do we
changes
make
in the
this?
wolf
Yeah.
model, how do we change wolf_df? So the way that would do, so wolf_df is actually it includes these error terms. So we added, a normally distributed error value to it. So what you would do is just create your own string, your own array of error terms for each chemical species and add it to the results from the simulation that you got. That would be the approach. And there are codes here that you can take a look at. If you look at the, I think it's concluded if in preliminaries, if we look at where these are come from.
You have a constant
guess-
section in there.
Yeah,
Is that-
these are
oh,
these
yeah,
are just
there's
the
wolf DF
constant
though.
sections, but it's what you have to do. Okay, so this get data over here is actually what it's doing. It's reading it from a file. It doesn't show how it's generated. It just gets data like observational data from a file. But there would be this whole, I mean, if this is a question, it's a separate, probably could have a separate short session about generating synthetic observational data, because that would be the answer here. Other questions? I don't see anything else in chat. All right, so let's see. I guess I'm on tomorrow morning. I'll be talking on 2 different topics tomorrow morning. The first one is cross-validation. So that's going to be about assessing the variability in your model, uncertainty in your model, and also potentially parameters. And the second part is on design of experiments. So after you've gone through all of this to create your model, estimate your parameters, make sure that your model is accurate, all that sort of stuff, then, now you want to actually get something out of this in terms of your science. And so how do you structure, the runs you're doing of the model in a way so you're systematically going to obtain useful results. So that's what design of experiments is about. Any last questions before we sign off for today? Let me stop sharing. Any last questions? All right, I'll see you tomorrow morning.